Skeptic, Graphs and Networks, the podcast exploring how the graph data structure has an impact in science, industry, and elsewhere. I was thinking it would be good today if I could put you on the spot and you and I do an episode about how one takes on a network project. Maybe we call it DIY network analysis or something like that.
Okay.
In particular, I want to pick your brain about the project I've been working on. I have all of the guests from Data Skeptic from 10 years of doing this. They're all in a database, and we've run them all through Scholarly and gotten their paper publications from there. And we've done a little bit with PDF extraction. So I have all of their publications, their co-authors, and we're crawling those. I don't know where my crawl will end. And then I also don't really know why I'm doing it in some sense, partially out of interest and exploring it.
What I think is one of the advantages of using network analysis is the explorative part, where we go into a project and we don't know what we'll get out of it. If we knew, we wouldn't have needed in the first place, right? we know what the answer is, but usually the challenge is not to get the answers, it's to get the right questions. And looking at the data from a network perspective gives you sometimes questions you didn't know you needed to ask before. So I'm all for your unexplored yet project.
Well, I have some exploration. I know the listeners won't get the visual, but let me share my screen. I'll show you a few things. We've got about 30 connected components in the network so far. But of course, I may crawl more. We're out 3 generations now.
How many seasons did you look at?
I took the whole 10 years of the show, even before we had seasons.
It's a sad view of interdisciplinary connections, I guess.
Sure, yeah.
When I'm thinking about it, the connected components aren't the same size, right? There must be. I get my guess is there's one big one, and the other are, let's say, medium size or something like that.
That's right. And I may have reported it wrong because I didn't count all of the people who are in a component of one. There are many of those. There are many people. Well, I've had many guests who, not many, but some guests who haven't published anything. And therefore they can't have any co-authors. So they're a community of one.
Right. I guess this would be the most common because they are the long tail. Because you use, let's say, a very different system when choosing people to interview. Usually you choose people by their publishing or their recommendations, but you use another way that lets you pick people from the long tail which many podcasts or other media don't get to, because they don't get the long tail because nobody knows them, right?
True. Yeah, a lot of our guest finding is through crawling the archive and a machine learning algorithm I built that looks at the abstract and tries to decide if it's a good fit for the season.
Without using, let's say, outside information like recommendations, citations, or something like that, or mentions on other media like, I don't know, a newspaper or so.
Right. So I do think that's one of the good features of the show. I have never invited on Jan LeCun or Yashia Bengio or anybody like that. There's no luminaries per se on the show. I'd rather hear from up-and-coming voices most of the time. Not to say that everyone's up-and-coming. There's a lot of established people, but they're not on television news programs like Jeffrey Hinton, stuff like that.
I'm here to stand for all the mediocre people you talk with.
So I'm used to data exploration in which the visual helps me a lot. When I asked NetworkX and Python to graph my data, I got this, just draw the network, put labels on it. Maybe I could remove the labels. I don't know. Its natural visualization is not at all useful to me. It's just sort of noise.
So when you're looking at a network, it depends on which size. Okay, if it's a small size, I guess the visualization will have more weight on your analysis. But if you're looking at a large network, sometimes I like to see the visualization, but it's not the main part, right? When you do visualization, there's the important thing is, of course, the layout. Okay, how do you apply layout? And there are many algorithms for layout. some of the algorithms, when you use the layout, gives you some of the answers in advance. For example, on a large network, I usually would like to use community detection, but some of the algorithms, the layout algorithms, applies kind of community detection by visualization. They cluster nodes that are close together, and when you see these different clusters, they usually correlate with community detection. I guess for large networks, I would usually use Force Atlas, which is an algorithm by, I think, Jacomi. Is the guy who made Gephi, the famous software network software analysis. That's in the case of visualization, but I think the basics is, of course, start with a connected component and look for the largest connected component, the GCC, the giant connected component, which is should be in most of the data, I guess.
So there I run into a problem actually. And it's not a bug, it's not an error, it is the truth of the data, but also an exceptional case. So there's a two-time guest named Morgeva, and one of the publications I interviewed her about, she was a co-author on, was called Big Bench. And it's an effort to tie together a lot of different benchmarks towards evaluating AI. And everyone who contributed a potential benchmark, she was one of 50 people, all became a co-author. So we have this singular paper in our data set which has 50 outgoing edges, and that has made her a natural community organizer in my data, and the node of most centrality and sort of this anomalous aspect will certainly be the most connected component as a result of that one fact.
What you call an anomaly is actually very normal when you look at a large network, right? The question is, and I think we should have started with it, is what is the network? Okay, what are you connecting? Are you connecting the papers, or are you connecting the authors?
So at the moment, and maybe you'll tell me I did this wrong, all of my nodes are authors, and an edge represents a co-authorship, that they were published on the same paper together.
Okay, so in her case, what you'll get is a complete graph, a click of 50 authors, right?
Yep,
Yeah,
exactly.
it's rare, but it happens, right? It's a long tail distribution. You'll get a click of 50, but most of the data will be, let's call it a click of one or two, right? That's not a click if it's a one, but you get the drift. Well, let's give it up for Morgeva.
Yeah, absolutely. Similarly, I tried to do some community detection using what Network X calls greedy modularity communities. I don't think it's Louvain, I think it's something slightly different. But although I get a wide series of communities, I don't know how to interpret it.
Louvain is based on modularity, so you should get probably the same result in the same area. When using visualization, and which layout did you use?
I played around a little bit with layouts, like here's the spring layout, which I believe is based on the physics principle of a spring, sort of how T-SNE works, where essentially nodes are going to be pushed apart if they're not closely related. But even still, I have hundreds of nodes here, it's hard to visualize for me.
Yeah, I guess there's one very highly connected node in the center, and all of the other nodes don't connect to any other nodes. So you get a like star-shaped network. Is that the case?
It's overwhelmed by the star look to it, I think, because of a couple more and a few, less co-authored up papers that I did. There are a couple papers with had maybe 15 authors that are impacting it. I think there are other relationships there. I haven't, I've interviewed people and interviewed their co-author under a different circumstance, but that fact doesn't become obvious from this visualization.
That's one of the reasons I like to use network analysis software, because you don't have to invent the wheel each time. You can just load the data very simply and then just choose from different layouts that are the best use cases. Usually, I would just load it to Gephi and play around with it. Can you show me again the one of the community detection? Is that the biggest connected component?
Building multi-agent software is hard. Agent to agent and agent to tool communication is still the Wild West. It's clearly the emerging future, but how do you achieve accuracy and consistency in non deterministic agentic apps? That's where agency comes in. They have a very clever spelling. Here's how it goes: AGNTCY. I'll give it to you again in a minute. The agency is an open source collective building the Internet of Agents. The Internet of Agents is a collaboration layer where AI agents can communicate, discover each other, and work across frameworks. For developers, this means standardizing agent discovery tools, seamless protocols for inter-agent communication, and modular components to compose and scale multi-agent workflows. Build with other engineers who care about high-quality multi-agent software. See where you can fit in this ecosystem. Visit agency.org and add your support. That's AGNTCY.org. Delete Me makes it easy, quick, and safe to remove your personal data online at any time when surveillance and data breaches are common enough to make everyone vulnerable. Like many of us who enjoy connecting online, I take my privacy and personal information seriously. Privacy protection has never been more crucial. That's where Delete Me comes in. Their team of experts specializes in finding and removing your sensitive data from data broker sites before it can be exploited by bad actors. In just one quarter, they reviewed over 3,000 listings containing my personal information. They're sending over detailed reports that show exactly what they found and what they removed. It's incredible how much exposed data they discover and protect, all while you're saving countless hours of frustration. Take control of your data and keep your private life private by signing up for Delete Me, now at a special discount for our listeners. Today, get 20% off your Delete Me plan by texting DATA to 64,000. The only way to get 20% off is to text DATA to 64,000. That's DATA to 64,000. Messages and data rates may apply.
Can you show me again the one with the community detection? Is that the biggest connected component?
This is the community detection one.
And you applied it on the biggest connected, the largest connected component, or by random?
I just passed it the whole graph, so I don't know what it does in that circumstance. I guess it must consider each of the components individually.
Oh, okay. So I guess if you used it on the whole graph, it would probably take the small connected components and make them each a community. And in this case, because the visualization is so dense, you can hardly see what's going on. What I would do is look at the degree distribution, okay, to see if there's, let's say, maybe if in the case of a paper with, let's say, 15 authors, and lots of people wrote with co-authored papers with them, I'll guess there'll be like maybe 10 or 15 high degree nodes, and all the other nodes will be like a long tail with just one or two connections. So if we can see the degree distribution of this connected component, we can figure out what's going on.
Good idea. That's not something I can rip up in 10 lines of code, but I'll do that for our next meeting.
Okay, cool.
And then you've mentioned this Giphy program. I'm not familiar with it. Can you share a few details on what it offers?
So Giphy is a product of Matthew Giacomi and other network analysis researchers that helps. It's a no-code software. You can upload CSVs or Excels, or now you can even. I think you can even upload streaming data or Neo4j, for example. And you can apply on the data many algorithms, network algorithms that are in the already in the software, from layout algorithms to centrality algorithms to community detection algorithms. And the cool thing is that the software keeps updating. I think there were lots of network analysis software out there, and I think in COVID-19 gave some a boost. They had they were locked in, they had time, so they updated the software. They updated it and made it a very updated many of the algorithms, and they had you can. I think 99% of what I'm using for analyzing a network I can do through Gephi. If you're a beginner, I don't know if I would use Gephi first. I don't think it would be my first choice. There are software network analysis software that are that are maybe web based and with simpler UX. But if you do lots of network analysis, yes, Gephi would be my go-to tool.
Would it be fair to say if you outgrow Network X in Python, you go to Giphy?
Network X, of course, has much more algorithms and you have much more freedom. But I think that coding is nice, but you always have to invent the wheel. Okay, you always need to decide on let's take your problem, which layout to use. So in Gephi, it's very easy. You just click a button and you can see the different layouts. Okay, so what centrality measures to use? Well, you have hundreds of centrality measures, but Gephi has the best practice ones.
So Gephy has it's a no coding solution, even though it's maybe weird to label it that. That feels very Web3. It's like a desktop app, but you don't have to know coding. I just load my data from Excel or CSV or whatever I got. It seems a lot better at visualization. That it's got a lot of good visualization stuff built in, and can get me up and running pretty quick without coding. Yeah.
Yeah, if visualization is what's most important to you, Gephi, I think, is the best network analysis software out there. It allows you much freedom with the visualization. Some networks have great layouts, but without freedom. You can't play with the parameters. Okay, but in Gephi you can play with all the parameters, and so it's a very cool app for visualization.
So I am personally starting to wonder if data visualization on graphs is meaningful once you get above maybe 20 nodes.
Yeah, of course, because as I said, I always want to see the visualization, even if it's 10, 100,000 nodes or so on. It gives me some intuition about the network. Let's say if it's assortative or disassortative. I mean, if it's like star shaped, if with many stars in it, like many high degree nodes that connect to each other and not to other leaves in the network, or is it like more of even out network? Okay, so the problem with Gephi, it can only show about I don't know, about 100,000, maybe 200,000 nodes. 1,000 nodes, let's say, or maybe 100,000 nodes, it would probably crash. So you need to use other network analysis software for it. But for networks this size, it would be nice to see the visualization. But if I can't, I would usually do the following process. First, I will look for the connected components. Okay, usually what I will look for is the giant connected component, because as we said, connected components are a long tail distribution. I will find the biggest connected component, and that's the component I would analyze. Then I would look at community detection, right? I use community detection to see how the component is built, what's its structure. And I'll look for the degree distribution to see, is it a fairly even network or is it a very skewed network? Okay.
I have some of those answers. That one in particular is probably obvious. The degree distribution is strongly skew. The modal answer is 0, that most people have, or there's a lot of people who didn't publish or don't have co-authors. And then 1, 2, 3, of course, declining. But it's very long tail, going out to at least 50.
Yeah, sure. So I guess you have I'm guessing let's say one giant connected component, and the other components are with very few authors in it. So I haven't published anything, so I'm in the long tail. Okay, and I feel fine. Most of us are in the long tail, so you can feel fine. By the way, I haven't told you it, but I will publish. I have.
You have a forthcoming book, yeah?
Yes, I signed a contract like on the 2nd of January. I sent them
Oh,
yeah,
congrats.
I sent them the PDF on New Year, and got a reply the next day. It's a good publishing, good publishing, and I know I know that books are the next big media, so I'll guess that's my way to success.
That's great, though. What language will it be published in?
In I'm biased toward Hebrew, so I guess
Well, we'll start there. Maybe its extreme popularity will demand an English release as well.
I'm bet I'm betting on it.
Good. Sounds good. Look forward to
Don't,
it.
but don't you bet on
All
it,
right.
okay? I can bet on it, but don't you do it.
So we've got In terms of my exploratory data analysis, connected components, look at degree centrality, look at communities, maybe with Louvain. The one that I also tried, mainly because it's baked in, we haven't touched on yet, is PageRank, which in my situation I found very boring.
It depends on the data set, right? Sometimes degree is nice, but let's say you're exploring a social network, an online network. I think it would be more interesting to look at in degree than just degree, right? Because I don't want to look at the spammers. I want to look at the people that are pointed to, the influencers. So I would use in degree, not just degree. PageRank, again, it depends because PageRank looks for nodes that other nodes are interested in. In your case, like in a case of authors, it might point to people that are very highly regarded but haven't published much. Of course, the PageRank will give you those with high degree, but the interesting thing, the anomalies in the network. After I'm looking for all the other stuff we talked about, the interesting stuff in the network is the anomalies. Let's say, what is an anomaly? In the case of centrality measures, one of the anomalies would be people with high centrality measure, high in one centrality measure and low on another one. Like in your case, authors with high page rank but low degree. So in this case, that would be a very interesting node, and it would point out to someone that is very, let's say, highly regarded, but didn't publish much. That's the one of the anomalies I would look for. Why is this the case? What's the story behind it? The good stories in the network lie behind the anomaly.
Interesting. Yeah, I did make one kind of novel observation. The highest page rank, even though I said it was boring, that my first instinct looked good. I said, well, who has the biggest score? And it was Yashio Bengio, a very prolific computer science AI publisher whom I've never interviewed. But what I didn't realize as I dug into that, of course, he published with someone who was on the show, is he's a prolific final author on papers. Like a paper comes out every couple of days where he is oversees the lab, I presume, and gave guidance and all that. But humbly takes the last position in the authors list, but is on a large volume of papers. So that was intuitive, but and he's regarded as highly regarded, so that made sense.
What you said is that he was the last author right on the list. So maybe we can give different weights to the people who are on the list. Like if you're the last author, you'll have least weight. That might show I won't say the true network, right? But the contribution network.
I like your idea, but how do I execute it with a variable length author list, which could be from 1 to 50?
You're using the anomaly on me, right? So it's because it's just one paper, let's say two or maybe even three papers from a list of, I don't know, hundreds or thousands of papers. It doesn't matter, right? If it's just one paper, even if you get it wrong, it won't affect the network as much, right? It's just one paper. I can think of many solutions, but even if they are not the best ones, this anomaly will not change the network in such a way that all analysis will be lost. There will be differences, but what I like about networks are they are very robust to data torture. Okay, so
I was about to use that word. Yeah, if small changes to my analysis produce radically different results, that doesn't say much about the analysis.
it's very hard to fool networks. Okay, I saw people try. I even saw people succeed, but it was very hard. It took them more energy. I think they could have spent less energy doing the right thing, but whatever. Sometimes it happens, but it's very hard to fool networks. I remember I get this question a lot when analyzing organizations. Okay, let's say people in the organization know you are applying network analysis on their relationships, and they need to fill out forms to say with who are their friends or so on. And they want to trick you into thinking they are hubs in the network, even if they'll fill out the entire organization, right? The entire people in the organization as they list out all the people in the organization as their friends. Still, the network wouldn't be fooled, right? Because I'll use, let's say, PageRank or InDegree, and I'll see that no one points to them, right? They just point to others. So the network wouldn't be fooled. It wouldn't be seen as hubs because the network has a long tail distribution, most of the things in the network fall in the long tail. Okay, I won't even notice them. So let's say the guy that wrote all the people in the organization would be just a connected component. Okay, a solely connected component, and let's say he has no friends. Okay, let's take the let's take the worst case scenario. So I wouldn't even notice it because, as I said, the network is robust and it's okay to tweak some things. It won't do it. It won't change the basics of the network.
Maybe I've set up my network structure in a suboptimal way. As we talked about earlier, my nodes are all the authors and the edges are the co-publishing between the two authors. Another way I could have done it where it would have been nodes are both authors and papers. And so two co-authors would be linked through a paper node that they published together. And I think that would get us something a little bit more like impact factor, which is done with a lot of journals and publications where you say, how many people have cited me? Not quite that exactly, but would that structure emit better results in some way?
Instead of doing a co-authorship, doing a citation network.
Well, citation network actually be too much work for me. I don't have the way to confirm. I don't have ground truth on all possible citations. I'd have to crawl all papers, right? I'm just crawling the papers of the authors I know. But in my current graph, every node is a person. I could have built a different graph where there were nodes of people and nodes of publications. And as an author of a publication, you would have a link to that paper.
What I thought you did was make a bipartite network, a network with two kinds of nodes: the nodes of papers and nodes with a type of paper and nodes with the type of person. And then you have in bipartite networks, you can each node, let's say node A and node type A and type B, can only be connected to each other. They can't be connected to same type nodes. So a person can't be connected to a person, only to a paper. And then you project the network. That means that you let's say eliminate one kind of nodes and base your connections on the assume connections between the nodes that are connected to the same type. So let's say you have three authors and that are connected to one paper. When you eliminate the paper, the three authors become a clique. Okay, they are all connected to each other. You assume the connection because they co-authored a paper, and then you get let's say each paper will make if you have more than let's say 2-3 authors, you'll get a clique. In the case of the large paper you talked about, you have a clique of 50. Usually, the problem with the bipartite network is that although it predicts the reality in more let's say specific way, okay, but it's harder to apply network algorithms on it because not all the nodes are the same. So when you get a high degree node, what does it mean? Does it mean that you have that it means that you have a paper with lots of authors? But if you apply it on the projected network, on network that has just authors in it, you'll get an author that is highly cooperative, right? So it means different things when you use bipartite network algorithms on bipartite networks, which I usually don't do, and I don't think people tend to use bipartite networks except for projection purposes. So I think what you did is okay.
So that's connected components, degree centrality, Louvain, PageRank. What else might I want to consider?
Okay, when you said Louvain, I'm doing the community detection. The question is not which algorithm to use. What do I do with the results? Okay, what do I do with the communities? Let's say the network is let's say a very large network. You have a big data. What I look at would be the communities graph. Usually, when we look at the network, like in the network I see before me, which I think it's a good thing the listeners can't see, is now saying nothing about the layout, of course. Usually, we see a network of nodes. Okay, and each node is like a person or a paper in this case. In a community graph, what I'm looking at is a graph or a network where each node is a community. It's actually an aggregation of all the nodes in the community. In this case, I can visualize the graph because there are much less communities in the graph, right, than there are nodes in the graph. So let's say you have like a network of 1 million nodes, but 100 communities. Okay, so I can see a graph of the 100 communities, and I can analyze it even visually. What I'll get is usually a connected component of the central communities. Okay, I can see which community is central, right? And a long tail of communities that are either small or not or disconnected. So I'll look for the giant connected component of communities. I would look for the central communities. I'll look for anomalies there. Like usually I expect the largest community to be the most central one. But what if one of the most central communities are a small community? Okay, it means that with let's say with less energy, they got a better position in the network. Okay, that's interesting. I wonder. I would like to know why. Sometimes it might characterize the entire graph. Let's say all the communities are geographically based communities. People in New York congregate with people in New York, and people in LA congregate with people in LA. But another anomaly I would like to find is homophily anomaly, right? If let's say all the communities are geographically based, but there's one community, the homophily is like, let's say, interests. Okay, they are all interested in something.
They formed around their love of data science, right?
Well, okay, let's. You're assuming that data scientists are friendly, right? But usually they are.
And uniformly distributed.
Their own connected components. But okay, let's say they cooperate together. Okay, they have a common goal. Why data scientists are connected together, not on the base of geography? I think we had this episode about the GitHub,
Yep.
and it sounded very logical when she said it was very interesting what she said, that the communities in the GitHub graph based on language, right, on computer language.
Right.
And it sounds very logical. It sounds very reasonable that people that code together code within the same language. But if she would have said that the communities are geographically based, we would say, well, that's very logical, right? People
Sure.
in the US usually cooperate with people in the US. People in Russia cooperate with people in Russia. Both are very logical, but only one is true. I think we talked about it, we mentioned it before, that sometimes when you analyze a network and you get a result, people say, well, that was obvious. Why did I need to do all the work? And then I asked them the same question. I asked them, why in Amsterdam you have more bicycle riders than in New York? And they think about it and say, well, in Amsterdam you have great roads, it's a flat country, it's people are very into environment, and people have bicycles. And you say all are very good reasons, but I'm sorry, I misspoke. It's the other way around, right? It's why there are more bicycle riders in New York than in Amsterdam. And they say, oh well, sure, because in New York you have many people, right? You have lots of people. Statistically, there will be more bicycle riders than in Amsterdam. And I say that's a very logical, very reasonable answer. And both answers are very reasonable, but only one is correct. Both are obvious, but only one of them is true. In this case, it sounds logical that they use the same. The homophily would be around computer language. In the other case, it seems very obvious that it would be related to geography, maybe human language, right? People speaking in English will usually cooperate with people in English, and people, let's say, speaking French would cooperate with people speaking French. So both are very logical, very obvious, but only one of them is true. And network analysis will tell you what's true.
Yeah, good story. I think it really articulates how we can have multiple interpretations, but there's only one truth, really. Well, I think I've got some good follow-ups to do here. Thanks to all your advice. Maybe we'll have a little part 2 where I report back on my findings.